Hello and welcome back to Calculus 1 section 3.8 on implicit differentiation. And now we get to use that chain rule we learned last time in every problem. So last two classes, we talked about the chain rule and we said that if you have function composition, you take the chain rule, and the chain rule is the way to take the derivative of the function composition, and you can get velocity, acceleration, or whatever the application is. Today is going to be a little bit different. So far, 100% of our problems were using what we would call a function. Y equals f of x. You took the limit of the function, you took the derivative of the function. You were always able to write function explicitly. So okay, whatever. Explicit function is y equals f of x. You are able to put y alone on the left, and then you have all of the x's in whatever order and combination they are on the right. So examples of explicit functions are y equals 3e to the x, y equals 2 sine x squared, y equals x squared plus 3x minus 1. So you know this is what your life was all about until now. Now we are getting into what we would call an implicit form. And these are generally not functions. And you get to recognize them because you will not be able to make it so it's y equals everything else. So implicit form is of the form f of x and y equal to 0. Now this notation doesn't mean a lot to you until we come up with some examples. One of the shining examples of implicit form is circle. So if you have x squared plus y squared equals to 9, this is a circle of radius 3. And because it fails vertical line test, if you are to draw vertical line anywhere, you see it cuts through twice, so not a function. You also see that you cannot write y equals everything else, because if you try to solve for y, you would get y equals plus minus square root of 9 minus x squared, and this plus minus is what ruins everything. So this thing over here, the equation is the implicit form. I'm just going to delete this so it's not confusing you. So implicit form, you will not be able to separate these guys. You have to be careful, because problem 3 equals x over y can be rewritten as y equals x over 3, so that's not implicit, right? Also, if you have, let's say, x equals 3 cosine y, well, you can rewrite this as y equals inverse cosine of x over 3, right? So there is a function that you can rewrite. So those don't count, right? Only the ones where you have situation where you cannot separate y to be alone is going to be your implicit. Otherwise, you do a little bit of this mathematical witchcraft over here and you get y equals everything else. So let's take a look at another example. say anything that would have a y squared definitely is in the bag. So x equals y squared, which is your sideways parabola, right? That's also implicit because you cannot write it as y equals everything else. What else? Say you have y cosine y equals x. Well, that's a good one, right? Because there is no way you can fish that y out. Because as soon as you separate one y, you trap another one, right? Yeah, I mean, you can try, right? If you try to fix it, you would say cosine y equals x over y. Presumably, you can divide by y is not 0, let's say. And now if you hit both sides by inverse cosine to free the y equals inverse cosine of x over y, and you just buried the other side. You see there is a y on the other side and it's a cosine? So there is no way to separate and make this y equal everything else. But if you are to put this into your graphing utility, you are still going to get a curve in space. And when you get the curve in space, well, that curve has tangent lines. And if there are tangent lines, then there is the derivative that makes those tangent lines. Which means we are able to differentiate this with whatever witchcraft, which is implicit differentiation. Right, so we are able to differentiate this, and we want to discover what is the method to differentiate something like that. Because do you have circular path? You know, maybe there is a roller coaster or something that you are designing. Maybe there is a racing track that is circular. I mean, if you have those ancient weapons for hunting, right? There we go. Perfect. That's a circle, right? So you have a lot of situations where the circular path is given, and now you have to differentiate that to find the velocity along that path. Differentiate again to find acceleration around that path, right? So there is a need, definite need, to differentiate these implicit forms, right? So that we can do the rest of the physics and engineering. So we want to figure out the way to do this. And we always keep in mind that y is some function of x. Even in these cases, they're linked. It's just that they don't have the property of y equal f of x like they have for explicit form. We have to figure out how to deal with those guys. So let's take a look at the derivative. All of the derivative formulas that you learned so far are going to stay the same, except they're all going to have y's now. And when you differentiate y, you still get 1, but it has to be multiplied by the chain rule, dy dx. So what we are going to do now is going to feel weird for some time, and then it's going to click and you'll be fine. So just, persist. Again, it's just so many of you, and then just like, it's amazing. It's amazing. Yeah, I know. Yeah, we really need someone to fill that chair there. How about we do the tug of war between two rows? I'll sit in that chair over there. So I'm still on this side. And whoever wins. It's a party. Yeah, but the other side has to pay. Yeah. All right. You're going to see everyone trying to fill that chair right there now. All right. So let's take the derivative of implicit form. Now I'm taking the derivative in respect to x. And let's say we are talking about the circle I mentioned earlier. First off, notice that the notation now has equal to 9 inside. We never had that before, because before you just put the equal here and you continue working. But now you have the entire equation right in there. Please listen what I'm saying and watch what I'm writing as I'm saying it. Vastly more important than you writing it down. Ready? Detonate that, please. No, just for this one example, and then you'll turn it back on. So, ready? Derivative of x squared is 2x. I took the derivative of x in respect to x. Plus, the derivative of y squared is 2y. I took the derivative of y in respect to x. The derivative of 9 is 0. We never had this before. Yeah, because dx divided by dx is 1. So when you take the derivative of x in respect to x, you don't have to write it. But technically, it was there every time you took the derivatives before. We never bothered writing it because we never had to think this way. One more time. The derivative of x squared is 2x. I took the derivative of x in respect to x. Plus, the derivative of y squared is 2y. And I took the derivative of y in respect to x. Equal 0. And now we just clean it up. This guy cancels because dx divided by dx is 1. And I have 2x plus 2y dy dx is equal to 0. And now you see that you can solve for dy dx, right? And that will be your derivative. So now we just need to do some algebra. So you have 2y dy dx is equal to negative 2x. Divide both sides by 2y. And here it is. Dy dx is equal to negative x over y when those 2's are canceled. And this is your derivative of the circle. Now you're able to find tangent lines. You are able to find the slope, right? You're able to measure the change. You're able to do the velocity, acceleration, and all of these kind of things.
Wait, why did it turn negative?
When you move 2x to the right-hand side, it becomes a negative. You subtract both sides, right? Okay. So it picks up a negative, and that negative stays. Just the 2's are canceled. And this is implicit differentiation. Now we're just going to make it insane because we're going to toss in all the other rules in. But if you are able in your head to go, I took the derivative of x in respect to x, they cancel. I took the derivative of y in respect to x, that stays. Anytime you have dimension mismatch, dimension y, dimension x. Isn't that you have the xy coordinate system, and this one over here is your y dimension, and this one over here is your x dimension? When I say dimension mismatch, I mean dy dx. We had the dx over dx. Well, those are canceling because they're measuring the same dimension. So, Calc 3, you just toss in z, right? And then you have more. Linear algebra, infinitely many dimensions if you want, okay? The linear algebra is that course that takes all of your mathematics up to and including differential equation and writes it in one single line. Can you imagine that? Yeah. One equation explaining all of the math you did for 3 years. Awesome. Welcome to linear algebra. Then you go, lecture 2. Let's take a look at more of these. So 3 cosine y squared minus 6x is equal to 2y, whatever. And we want the derivative in respect to x. All right. Differentiating. Derivative of cosine is beautiful. So negative 3 sine y squared. And now I have to use chain rule to multiply by 2y. Because y squared, right? Right. And then I say I took the derivative of y in respect to x. When you are done with differentiation of the term, then you hit with I took the derivative of y in respect to x. Minus derivative of 6x is 6. I took the derivative of x in respect to x equals 2. And then you have again dy dx on the other side because you took the derivative of y in respect to x, and that will not cancel. So now what I have is that dies, and all I need to do now is to massage this with algebra a little bit to get dy dx alone, and all of the rest of the garbage goes on the right. So the first order of business is to move all dy dx terms to the left and all of the terms that have no dy dx to the right. Now in our case, we get to have negative 6y sine y squared dy dx minus 2 dy dx equals to positive 6, right? When you cancel this dx, negative 6 stays alone. Kick that to the other side, and you have positive 6. Now, what's the obvious step to get dy dx alone? I heard it. Someone said the F word. Yes, factor. Good. So, factor dy dx, and then you have negative 6y sine y squared minus 2 equal to 6. And then dy dx is equal to 6 divided by negative 6y sine y squared minus 2. And just because you're not noobs, you cancel the 2, right? So it becomes, and you put the negative up there as well, 2y sine y squared plus 1, right? Just because you can. There you go. That's the derivative. And if you give me a point, I will measure how steep is the tangent line, which measures the change at that point. It measures the velocity at that point, measures acceleration at that point, measures the marginal cost at that point. All of the application that we had so far now can be computed because I have the derivative, right? Was this a function? No. All right. Three x to the fourth minus 4y to the sixth equal to 2xy. The derivative in respect to x. Yes. I put something like that on the exam and I just beat it. I would too. It's just a massacre. Why did I write it's a trap? You can do it? You can. It's implicit differentiation. Applies to anything.
Yeah. It's not applied to dx.
You have to take the derivative of every term all the time.
But only x on the right side.
Yeah, what's happening with the right side?
Nope, that's why it's trapped.
It would be dxy over dx.
Nope.
Is it?
It isn't. That's why I wrote in red, in blood. What's on the right?
Oh wait, so
Product rule!
Yeah.
Nice! Pause. You have to do product rule. Yes, the chain rule, product rule, and quotient rule all weave their evil ways into this. Okay? So you have to be careful. So we have over here a product rule between a function 2x and a function y. So you get to copy the first derivative of the second, and you follow with appropriate chain. Copy the second derivative of the first, follow with the appropriate chain. Massacre on the exam.
this is part of the open.
Most likely. Most likely. I mean, XY is so common to be on the exam, on the implicit, that like kind of hard to escape it. So the derivative of 3x to the 4 is 12x cubed minus 4 times, oh, I forgot dx over dx.
You have to put dx.
You do not, but
Only
we're
when it's a y.
still babysit. Yes, with dy dx you absolutely have to, right? 4 times 6, 24, y to the 5 dy dx, because we took the derivative of y in respect to x. Guys, over here is clearly stated, what are you taking derivative in respect to? You're taking derivative in respect to x. Your every denominator better be dx. Equal to, and here is the trap. Copy the first derivative of the second times dy dx, because I took derivative of y in respect to x. Plus, copy the second, which is y, times the derivative of the first, and I'll put dx dx because I am taking the derivative of x. So now I can point to this term like that and say product rule.
So you have to put it after each.
Well, over here I took the derivative in respect to y, so derivative of y is 1.
Yep.
So, and I took derivative of y in respect to x, so dy dx survives. Over here I took the derivative of 2x, which is just 2, dx dx, it's canceling, so. All right, now we do some algebra here. We have all of the terms with dy dx on the left. So negative 24y to the 5 dy dx minus 2x dy dx equals to 2y minus 12x cubed. I hope that's good. So all of the terms that have dy dx, they go on the left, because the next step is to factor it, right? dy dx, and then you have your negative 24y to the 5 minus 2x, and on the right hand side you still have your 2y minus 12x cubed. Divide both sides by the bracket you want to get rid of, and you have your dy dx equals 2y minus 12x cubed divided by negative 24y to the 5 minus 2x. Now we definitely want to bring this to the boss level, right? Right? We can cancel 2's everywhere. Each term is divisible by 2.
Yeah.
So how about we divide top and bottom by 2 and reduce it? And also, work out the minus sign from the denominator on top. So it's 6x cubed minus y. You swap those terms to absorb the minus, and then you have your 12y to the 5 plus x. And before anyone's head explode, a minus b is negative b minus a. So if you are to swap the terms, that's what I did. I swapped those terms. On top, it generated minus, and that minus killed those minus in denominator. It's called flexing in mathematics. You got x plus 12 y to the 5? Yeah, it's commutative, right? So addition. What's 2 plus 3? And 3 plus 2? And 2 plus 3? And 3 plus 2? 6. So yes, it's commutative rule. So it doesn't matter for addition which order you put them in. You can even swap the top if you are willing to write negative y plus 6x squared, but we kind of don't want to start with the minus sign because it freaks people out. Not as much as clowns, but it's up there. Let's see something else. What else cool can we come up? Oh, we didn't do any e's. Let's not discriminate. The derivative in respect to x of e to the y minus 3 plus 6x divided by y squared plus 1. Oh, equals, oops. Equals to, let's just put a number. What number should I put? 10 it is first. First come, first serve. You know the rule. Did we say no coffee? Yeah, we did, right? Okay.
I thought you said no coffee for me. What?
No, why no coffee? Some people, I mean, do you know what his level of blood in coffee is? It's like 2%. People from Colombia.
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 Colombia. I don't want to kill somebody today.
Know the ropes. Been burned before.
Ready. What's happening?
Ask me what I did when he called the next one.
Perfectly fine count. Does this actually help or just work?
YDX.
Oh, shit. That's chain too. Because you have e to the y and
Yes.
3, so that's.
Oh, you know, but it's still this one.
Yeah, it's just y.
Finish it off first. I'm still here. Quick thumbs up. People have died for less. Why do you think I with a good time? Why do you think I have to move? All right, so what do we use, guys? Quotient. Product rule. Oh, by bringing this up to the -1 and then using the chain rule? Nice, nice. Then the quotient rule, nice, nice. Yusuf, you have an idea. Well, do the boss move, come on. I wanted to show off the boss move, but then he figured it out too, so I don't want to steal his thunder. Well, now you have a notebook, I can't, well, I still can't draw it. Take notes. Copy.
So why they're like cross multiplied? So
He killed the quotient and the product and the chain by cross multiplying the denominator into 10. Right? Cross multiply. It kills the quotient rule. You don't even have to worry about the product, and you just take the derivative of each term independently, and done. So now the derivative of e to the y minus 3 is e to the y minus 3. Chain rule kicks in to take the derivative of y minus 3, which is 1, and then you have dy dx because you took the derivative of y in respect to x. So that one might be a little bit tricky if you're not used to it yet. The rest should be straightforward. Making sure you're placing dy dx where it needs to be.
I apologize for my family.
Don't apologize. No apology.
So how did you multiply by?
He took the denominator and multiplied into 10, right? Because you can multiply both sides by y squared plus 1. Right? I know. Woo! Look at that. So cross multiply. Oh, I neglected our audiences. Millions of people watching the live stream. So the trick is to cross multiply. So dx ddx of e to the y minus 3 plus 6. equals to 10y plus 10. I know, right? Just 400 years ago, I'd be burnt on a stake. So, I know. I'm gonna take the picture later on with this one for your social media, right? We have e to the y minus 3 times the derivative of the exponent is 1, and then we took the derivative of y in respect to x plus 6 equals to 20y dy dx, and then plus 0. So now we have dy dx, and in parentheses e to the y minus 3 minus 20y. On the other side we have negative 6, and the derivative dy dx is equal to negative 6 divided by e to the y minus 3 minus 20y. You could get rid of that negative by swapping the denominator, right, using the same trick. So 6 over 20y minus e to the y minus 3. That's just some further flexing that you can do. Yes. Yeah. It's just wait, you computer science? You're thinking about being computer science. So no, the first one is wrong. If you were electrical engineering or something, I just give it a pass. But would you agree that this one has one operation less than the previous one? On a 10,000 calculations, that's 10,000 operations done less. This is why computer science doesn't get a pass on not doing that, right? Because you optimize the software to work faster by having the most simplified answer. Where electrical engineers, they just don't care, because it doesn't really matter whether you're going to punch an extra, for the single calculation you do in the calculator, right, once, then it doesn't matter which one you use. But if you're programming computer to do 10,000 calculations like this, right, to compute something, then that minus sign or this one is difference in efficiency of the software. Yes? Yes, we did use the chain rule, which is where the 1 comes in. The derivative of e to something is e to that something, right? Because it's itself. And then the derivative of the top is, the derivative of y is 1, and the derivative of minus 3 is 0, right? So I just have 1 there. And then I took the derivative of y in respect to x as a chain. So I do have two chains, one for the exponent and one for the function itself, right? So they're all there. Cool? No. Nice. So now we know we don't have to do quotient rule ever again. Nice, right? We didn't put any square roots, so I kind of feel bad. So the derivative in respect to x of square root of 3y plus, how about some 6 over x over there, equal to should we make it terrible?
Yes.
Say no more. Tangent xy. Sponsored by Mets. All right.
God damn. Semi-automatic.
Semi-automatic sneezing.
Supposed to be 7, you did 6. Okay? Yeah. Okay. Still breathing. Still breathing. 3 times 5 and 10 times.
one more example after this. Take a break.
Yeah, no, it doesn't know. That's
This one is high spice level, right? What's the derivative of tangent? Secant squared. And then you have to have secant squared xy times the product rule as a chain, right? So that's that spicy add-on. So it's not just product rule, it's actually product rule inside the chain. All right, so the derivative of a square root is 1 over 2 square root, which is 3y, times the derivative of 3y, which is just 3, and I took the derivative of y in respect to x, plus the derivative of this is going to be negative 6 over x squared, dx cancels, equal to, and here is the spicy term, secant squared xy. So this is the derivative of tangent is secant squared. So you have to start with whatever is in here gets copied. You have to start there. And then because it is not a basic function, inside the chain you get to do the product rule. Remember the trap? That's the same one. Copy the first, derivative of the second, plus copy the second, derivative of the first. And now we just need to do a lot of algebra to clear this up. So I have 3 over 2 root 3y dy dx minus 6 over x squared. And here I have to distribute, so I have x secant squared xy dy dx plus y secant squared xy. All right, meditate on this for a while. We good? Now move all dy dx term on the same side, factor out dy dx. So we have 3 over 2 root 3y minus x secant squared xy. Dy dx is factored. On the other side, y secant squared xy plus 6 over x squared, which gives us dy dx is equal to, and now you have your y secant squared xy plus 6 over x squared divided by 3 over 2 root 3y minus x secant squared xy. What's the issue?
X squared.
X squared in denominator. And what else is issue?
Root 3y.
Yep, 2 root 3y, exactly. So, what do I have to do? I have to multiply x squared 2 root 3y and 2x squared root 3y. I have to multiply this in, make it orange, so I can kill those denominators. We kill the double fraction. So dy dx is equal to 2x squared y secant squared xy plus x squared cancels 12 root 3y. On the bottom, cancel, 3x squared minus 2x cubed root 3y secant squared xy. Yay. So you make the common denominator, right, with all the, right, with everything, and then multiply, cancel what you can. So there nothing cancels for the first term over here. So that's why we have a 2 and x squared and the y and the secant. For the second one, x squared cancels, so 2 survives, times 6 is 12, root 3y, and the same on the bottom. I did say one more example, but then I forgot about the other levels. So we'll have to do a couple of more. Let's take a breather and go with x squared plus y squared minus 1 cubed minus x squared y cubed equals 0. Derivative in respect to x. Now we have a chain rule, right, and a product rule.
about the applied problem, but one is I'm a lot sure. Yeah, no. No. This one's not where that's all right, this is old. It's talking about the guy, maybe the pixel. You're saying that next week will be the next. Yeah, maybe.
All right, let's take a look at this derivative together. We start with 3 stuff squared. So 3 stuff squared, that's the derivative, right? And then the derivative of the inside is 2x plus 2y dy dx minus 0. And then we have the product rule. Copy the first, derivative of the second, then dy dx. Plus and minus will give you another minus there. and then you have copy the second, derivative of the first, and then equal to no copying 0. So we multiply this out and order the terms. We have 6x x squared plus y squared minus 1 squared plus 6y x squared plus y squared minus 1.
Yeah. Shouldn't that be y cubed?
Where?
The last one.
Oh yeah, the last one should be
Up top?
y squared.
Y squared.
This one?
Yeah,
Yeah.
right? Shouldn't that be?
It is clearly y cubed.
Alright.
Obviously. Thank you.
I was like, damn it.
Now I gotta start all over again. 6y this. Okay, good. dy. No, seriously, that's important. That will mess things up. Minus, and this is a very important applied problem. 3x squared y squared dy dx minus 2xy cubed equal to 0. We got it. Put the notebook sideways. Get the dy dx terms together and then divide it into the right side. So what goes on the right is 2xy cubed minus 6x x squared plus y squared minus 1 divided by, this is already on the left, so 6y x squared plus y squared minus 1 minus 3x squared y squared. What happened?
The 6x and the 6y.
When I multiply this one, 2x into 3, I get 6x, and I multiply 2y into 3, I get 6y, right? Distribution, because this thing distributes to both terms to get the two separate terms, because one of them has dy dx, the other one does not. So I have to separate these. All right? I call this applied problem. Why? Well, you get to find the tangent to the curve. Let's see some application here. So, I'll wait for you to finish writing first. I'll take a picture of this. I'll post it. Yeah.
6x.
Oh, I missed the squares. Yes, that's true as well. I missed the squares in the answer. So there is a square and a square. I missed these two squares when I copied. So now I added those two squares on the bottom. So find those. I was just testing everyone to make sure that, you're paying attention, and being that, you are so diligent, obviously you're not going to miss it. The rest of you. All right, so let's see the application. So I already typed the function in Desmos, and all I need to do is equal to 0, right? You check, see that the function that I gave you is that one.
Yes.
Right? And I put the 0 in now.
Aww.
I know. All right? So now you can find a tangent line in 1, 1.
3 fingers.
See that?
Hey.
How awesome. Now we're going to do some men empowerment tonight. So you got to sit out for like 2 seconds. It's not a big deal. You write her dysfunction, and if she has no clue what this is, she's not for you. Walk away. Right away. That's it. So you're done right away, right? You don't need to write anything. It's just this. That's it. It says everything. right? Far better than anything else. And the piece of paper, you can do the wrapper too. It fits. You see the gum wrapper? Fine.
For Valentine's Day, I'm just gonna write that in the card and like bam.
Exactly.
What do I do with this?
You will immediately know on the 14th. Because if she starts graphing it, at least you know it's a keeper. All right. Now 100% of the classroom is back. Hello, welcome back, everyone. Let's go with the second order. Can you imagine that you can take a second derivative here? I know, but not on this problem. No. I mean, you can, but the course ends in December, so let's do something. Let's do the circle, okay? Find d2 dx2 of x squared plus y squared equals to, let's say, 16. This means you have to find the first derivative, and once you are done and you have it dy dx equals everything else, you have to hit it again. It will be negative x over y, then you get a derivative.
How much are we supposed to do?
Oh,
Y squared?
I have to do it.
think there's supposed to be some meteor shower or something tonight. You look up, you're supposed to be able to see it. Yeah. What time? I know, I thought I saw it on Facebook. Yeah, sure, probably.
All right. So we first do one derivative, then we do another derivative. So I'm going to peel off one derivative, and one derivative is going to be applied to get 2x plus 2y dy dx equals 0. And then we solve the inner derivative into dy dx equals, no coughing, negative x over y. This is what we had before. Now you see that when you apply another derivative here, d times d becomes d squared.
What happened to the 2's? You have
2's cancel, right? Because it will be 2x over 2y. So 2's cancel. There will be a 2x and a 2y, and then they cancel. All right, so now d times d is d squared y over dx times dx is dx squared, and that's the second derivative, equals 2, and now we have a quotient rule. If you cross multiply, you get a product on the left, so you don't really save much. You can put y to the negative 1, then you have to use chain rule, so you don't get to win either way, right? You have to do stuff. So y squared, then you have your y, and then negative 1, and since you took the derivative of x, it stays, minus copy negative x, and then take the derivative of y, which is dy dx. So now we just need to, fix this. It's already equal to the second derivative, which is awesome. We just need to clear the mess in here. This is negative y plus x, and now this dy dx is equal to negative x over y. Plug in. So I'm just going to leave it as orange, negative x over y over here, and I still have y squared. By the way, there is a third, the derivative, and the fourth and the fifth after this, so if you feel like it. Right, let's say you get home and you can't sleep. Trust me, by the time you get to the fifth derivative, you're out. Right? There's really no excuse, any of you, to suffer ever from insomnia, because you can just keep doing derivatives until you physically pass out. Negative y minus x squared over y, the y squared. Multiply everywhere by y to kill the double fraction. And you have a negative y squared minus x squared divided by y cubed. You can pull, well, now it's just flexing. Pull the minus out. You have x squared plus y squared divided by y cubed. Some bleach. And that's it. I hope you're not disappointed. It's implicit differentiation. We are going to use this for word problems in 3.11 called related rates. Very important stuff. Just to give you a preview of what's coming up using these implicit differential formulas, say that the volume of the sphere is given by 4/3 pi r cubed. And you are supposed to take derivative in respect to time because you want to look at the rate of change of volume in time and the rate of change of radius in time. If you have a snowball sitting in the sun, while in the heat, it will start to melt. It loses volume in time, and it also loses size, which is radius in time. So we can actually relate those and see, calculate one loss in respect to the other loss, because, in engineering, generally there are certain things you can measure and other things that you can calculate through these kind of relationships. So 3.11 is actually a money-making section if you are actually going to be engineer, right? You will be calculating. So now you say derivative of v is 1. I took the derivative of v in respect to time. Over here, 4 pi over 3 is a constant. Derivative of r cubed is 3r squared, and then I took derivative of r in respect to t. 3's are canceled, and now I have my, guys, this is 3.11 calculation, but it's implicit differentiation. Now I have 4 pi r squared dr dt, and you have related rates. Rate for volume related to the rate of change of radius. So that's 3.11, which we will talk about next Thursday to close off the chapter, to close out chapter 3. So please, invest a lot of time to learn this implicit differentiation. It is coming back in Calc 3. It is coming back in differential equations. So you will see this again, not just 3.11. We'll take the short break. When we come back, we will talk about tangent lines. We are going to calculate tangent lines, the slopes, functions, and all of that stuff. So, see you about 300 seconds.